you don't even get to do the partial fraction decomposition on this. Okay, so the thing is, this is irreducible. That means that doesn't factor into two pieces. I mean, 8 and 4, no, 8 and, it'd be 8 and 5, which adds up to 13. If that was a 13, then yay, that would work, you know, and then we could do, then it wouldn't be so bad. So let me go about it this way for this problem. It's a good idea to sometimes think about, okay, so you really can't do anything with the denominator, but you can manipulate the numerator. And so what you should ask yourself is, you know, what if I could change this numerator into something, you know, what would be a good thing to change this numerator into? Okay, so, and perhaps, anybody have any ideas? What would you like to change the numerator to? If you could change it to something, what would you like here? It would make it really easy to integrate. Can you guys hear me, by the way?
Yes.
Okay, great. I was just wondering. Nobody has any idea? And what would you choose for this for the numerator? Okay, ignore this problem completely. Except, you know, that this has the same denominator. What would be really good?
I don't know. I was thinking either like the same as the denominator or like 1, but I don't know.
Like a 1, or the same as the denominator, so that it reduces to 1. That would probably be the best choice. Or maybe a 1 in the numerator. Those are actually pretty good choices. Yeah, I guess my question was not that great, but what I was looking for is, can you imagine if this was the numerator? Can you see how that would work out if 2x plus 12 were the numerator?
Oh yeah, because then it's just dx.
Yeah, because then that would just be the derivative of the bottom part, and so then then when you integrate it, it's just going to be the natural log of x squared plus 12x plus 40. Boom, you're done. Plus a constant. Okay, that would work out that way. Okay, so what I'm gonna do actually is this. So 2x plus 12. Also x plus 6 would also work. X by 6 would also be good. Okay. And also 1, like Liana said, would be really great. Okay. So I'm going to put x plus 6 there. Okay. I'm just going to change it to an x plus 6. Okay, but if I do that, then I'm not allowed to put an equal sign. Boo. But that's okay. I can still put a 3 right there. Like that. Okay, so you see that this is equal to all this, right? So I just put an x plus 6 here, because that's going to be really nice to integrate. And that gets rid of the x part. So then I just have this part here to deal with. And for that, we'll do the integration later. We'll just leave that right there for now. This part right here, when you have this a constant over a quadratic like this, then what you should do is complete the square here. Okay, so if this was x squared plus 12x plus 36, then this would be a perfect square. It's x plus 6 squared. Okay, but it's not. I have to put the plus 4 there to make it 40. So 36 plus 4 is 40. Okay, I'm just gonna put ditto marks for this one. No, I better write it out. Don't get lazy now. actually. Okay, and then this one is 3 over x plus 6 squared plus 4. Okay, and now I'm ready to integrate. The integral of this is just going to be 1/2 natural log of x squared plus 12x plus 40. This one right here is actually this. So there's a formula on the front page. But I just had an x squared plus a squared, 1 over x plus a squared. The integral of that was the inverse tangent. What was 1 over a times the inverse tangent of this over a. Okay, so for this part right here, I'm using this formula here. Okay. So I had a 3 in the numerator, and then instead of x squared, I had x plus 6 squared. And then here, so this is a 4 here. So a is 2. A is just plain old 2. And then instead of x, I put x plus 6. Okay, so that's number 8 from 7.4. Any questions about that? Wait. Okay, let's move on to section 7.5. So 7.5 is sort of a review of the other sections that we've covered up to this point. It's just strategy for integration, just an overall integrate strategy. And the thing is, when you have questions on the exam, you're not going to know which section the question comes from. And so you have to approach each one and try to figure out how you're going to integrate it. And of course, you can use the techniques that we've done before, but it's not going to be, you're not going to know, oh, this problem is from the section on integration by parts, so I should look for integration by parts. Or this section is from trigonometric substitution, so I should look for that. Okay. So here's just a few guidelines, and then each problem is unique and is going to present different challenges. But here's some guidelines. You want to simplify the integrand if possible. The integrand is what you're integrating. And then look for obvious substitutions. Those are U-substitutions. That's what you need to look for those. And then also you can classify according to form, and that can help out. Okay. So at this point, we haven't learned a whole lot of different techniques. So you can kind of go through each one and see if it's going to work out. Okay, so let's do some examples. Here we have the first one right here. And what do you think would be a good way to tackle this one? Wow. Any suggestions?
Would it be integration by parts?
Yes, integration by parts. If it has a logarithm in it, then, and it's just like in this product form right here, then integration by parts is a really good guess as what to do, okay? And this has a logarithm and it's multiplied there, so, and then you let u be the logarithm, Okay, so du becomes 1 over y dy, and then dv is the rest, which is the square root of y times dy, or I'll write it as y to the 1/2 dy. So that means v is going to be y to the 3/2, 2/3 y to 3/2. Okay, so and this product right here is going to be what we need to be able to integrate, and that's not going to be too bad. If you multiply this with this, that's not too bad. Okay, so the integration by parts says you go uv, and you're going to evaluate from 1 to 9 minus the integral from 1 to 9 of v du. Okay, that's integration by parts formula. So we'll go ahead and with the uv first. That's this times this. Integrate from evaluate from 1 to 9 minus the integral from 1 to 9 of this product here. Okay, y to the 1/3 over divided by y, that's going to be y to the 1/2. Let's go ahead and evaluate this. So you put a 9 in, that's 9 to the 3/2 log 9 minus something log 1, and log 1 is 0, so the minus is going to be 0. Okay, minus, and then here integrate this. So this means you raise that 1/2 to by 1. 1/2 plus 1 is 3/2. You have a 2/3 there. You're gonna have another 2/3 because this when this 3/2 comes down, something needs to counter it so that you end up with just that. So you get that. Okay, 9 to the 3/2 is well, you do this. Well, let's apply the square root first. This 2 in the denominator means to take the square root of that, so that's going to be 3 to the 3rd. Okay, and this is going to be, that combines to give you 4/3. And let's put a 9 in here, and that's going to be 3 cubed minus 1. Okay, so putting a 9 in here, it's the same thing as this, so it's 3 cubed. Okay, so that reduces that to 2, so you've got, what is it? 3 squared 9, that's 18 log 9 minus 4/3, and this is going to be 27 minus 1, so that's 26. And I have 18 log 9 minus 104 over 9. For 9ths. I can't believe that. Okay. Any questions about that? So the key here was that it's a logarithm again and multiplied. Not just that it's a logarithm, but multiplied, you know. Okay, let's look at number 2. And what do you think, how do you think we should tackle this one? I'll let you guys think about it for a few seconds and see if you can come up with an idea, any suggestion.
Would it be the integration of by partial functions? Or would by parts be better?
I'm trying to think. Partial fractions. What does the denominator factor into? Oh, wait, what does it factor into? It doesn't factor into anything that's very nice, but you could, I think, yeah, you could do partial fractions because the denominator has to be able to factor. Yeah, but it's going to be kind of nasty. There's an easier way. Integration by parts doesn't work very well. Because if I let this be my u and then this is my dv, then it's going to be hard to integrate. Or if I let this denominator be my dv, let the denominator be my u, and this be the dv, then when you differentiate 1 over t to the 4th plus 7, that's pretty nasty. This one, what you want to do is look for a substitution. And maybe it's not that clear. It's probably not that clear. But if I let u be t squared, then my du is going to be 2t dt. Okay. So this is a U-substitution. I'm not doing integration by parts. So that means that the t dt is equal to du over 2. So this part, all this right here, turns into du over 2. I'll put the 1/2 out there. So du over 2. And then u is t squared. So what I'm going to end up with here is u squared. Okay, so u squared is t to the 4th, and that becomes u squared. Okay, so the t dt becomes du over 2, and the u squared becomes that. Okay, and then here, this one right here is, you can use this formula here. So here we had u squared plus 7. So that means a is the square root of 7. So you put the square root of 7 there and the square root of 7 there, and then u's there. So 1 over root 7 times the inverse tangent of u over root 7 plus constant. Let me put parentheses around that. So you can't leave the answer on u's. You have to put it back into the original variable t. So this is going to be 1 over 2 root 7, combining those two. Inverse tangent of, and then the u is t squared. So you got to put a t squared back in over the square root of 7 plus a constant. Okay, great. Any question about that? Okay, let's move to the next one, number 3. So you kind of look for patterns, okay? Any suggestion on what to do, or do you see any pattern here that could be helpful? Does anybody recognize secant tangent?
Isn't that the integral or derivative of secant x?
Yes, that's the derivative of secant. So the derivative of secant x tangent x. No, I'm sorry. What am I doing? So the derivative of secant x is secant x tangent x. Okay, so you can exploit this, or it's possible that you can exploit this by doing integration by parts. Okay, and letting all this be the dv part, and then the u part will just be this x. So then du is just dx, and the v would be secant x, like that, because we can see that the derivative of secant x is all this. So make that my dv. That way my v becomes just secant x. Okay, and so here's there's the formula right there. Plug everything in, u and v, so that's x secant x minus the integral of, and then v du, that's just going to be secant x dx. And there's a formula for the integral of secant x. Let me go back to the first page. It's right here. Here's the formula for integral of secant x. So just use that formula to gloriously finish off the problem. Yay. So the integral of secant x is natural logarithm of the absolute value of secant x plus tangent x. And then, of course, put a constant on the end. Okay, so that's number 3. Let's go to number 4. This one looks a little bit tricky. And at first you probably think, whoa, what the heck? You got this 7e to the 4x plus e to the 4x. So that looks kind of complicated, right? Okay, but one thing that you should recognize is if you have a to the m plus, if you have an exponent like this, it's a to the m plus n. Do you guys remember how to rewrite this?
Is it a to the m times a to the n?
Yes, that's a very important formula about exponents to remember. And so we apply this formula to this problem because e to the something, that's just exponent stuff, right? So it's 7e to the 4x, e times, just applying this, e to the 4x times e to the 4x. Okay, so this is e raised to the e to the 4x. Okay, now, here you can kind of just use a substitution. The way to do it would be e to the 4x. Wait. No, e to the 4x could be the substitution. Okay. And the derivative of this would be this itself times the derivative of this top part, which is just 4e to the 4x. Okay. But like I always try to do, I always like to just guess at these. Okay, but you can do that, and then you can go, oh, du, it's just going to be e to the 4x times the derivative of this part, which is going to be 4e to the 4x. The derivative of 4x is e to the 4x times the derivative of 4x, which is 4. Okay, so in other words, the derivative of this would give us this piece and give us this. It would also give us a 4, but we don't want a 4, so just divide that by 4, and we're done. Okay, so the derivative of this would be exactly that, because the 4 there will be a 4 there, but that gets canceled out with this 4 in the denominator. Okay, let's look at number 5. Okay, this one should be a little bit more clear about what you should do, but what do you think? What should we do here? Okay, do you notice something that appears in more than one spot?
The natural log.
Yeah, so you have the natural log's right there. Natural log's also right there. So when that happens, and natural log's is a pretty complicated thing to integrate. If there was just one natural log and we didn't have any denominator and we had a bunch of other stuff in the numerator, then it would be integration by parts, with u being the natural logarithm would be a good thing to try. But that's just not going to work here because we have in the denominator. So when that happens, you do a U-substitution. When you've got something complicated that appears in multiple places, then that's a good candidate for a U-substitution, okay? And another thing is this right here, this du, is actually this and this. Okay, so all this gets changed into the du. (15u) over, and then all this is your du. Okay, it's 1 over x dx just becomes the du, and then here we have the square root of 4 plus u squared. And then for this one, I like to write it this way. So 4 plus u squared to the negative 1/2. So 1 over the square root of that is to the negative 1/2. Okay, now take this part right here. You can see that the derivative of this inside part is 2u, and there's our u. So this is how you want to proceed. Raise this by 1 power to that. Now, if you take the derivative here, you're going to have a 1/2 come down, and you're going to have a 2u come out. The 2 and 1/2 are going to cancel each other, and there's your u. So, and then this reduces by 1 power, so you get 4 plus u squared to the negative 1/2. Okay, so this should be the answer right here. Any questions about anything so far?
You leave it with the u. You don't have to change it.
Oh, what am I doing? Yes, we're not done. So the u has to be changed back to a natural log of x. And also, while we're at it, this is to the 1/2, so we'll change that back to a square root. You don't have to. Okay, great. Let's go to number 6. Okay, this one is, ooh, this is pretty nasty. Because you have 1 plus the square root of x to the 8th. Now, if the derivative of the square root of x involves 1 over the square root of x, right? Because if you take but there's nothing like that outside here. So you can't just make a U-substitution here and then do it. This doesn't, there's no clear way to doing that. This one, this is kind of hard to see intuitively how you work this. But if you do this, make u equal to 1 plus the square root of x, okay, which is this inside part right here, then du is going to be, okay, the derivative of this will be 1 over 2 root x. Dx. So you make that substitution right there. Okay. For this particular problem, I think it's going to be easier if we evaluate these limits of integration right here. So when x is 1, u will be, if you put a 1 in here, you put a 1 in there, then u is going to be 2. And if you put, and when x is 0, you put a 0 in here, u will be 1. Okay, so the limits switched from 1 to 2. That means we don't have to ever go back to x's. We just finish the problem in u's, because there's our limits of integration. And we have a u to the 8th. Okay, now, here's the tricky part. You got this dx right here. How to handle that? Okay, so you come down to here. We can solve for dx here. That's going to be 2 times the square root of x du. Okay, but we can't just put this right here because that has an x. We can't have any x's. Okay, so what you want to do is you want to take this right here and you're going to solve for, because this is a square root of x, so we'll solve for a square root of x. Okay, and we have the square root of x is going to be u minus 1. Okay, and then we put this into there. Okay, so we have 2 times u minus 1 is equal to dx. And then this one goes in for the dx. Okay. Okay, so we have a du. Everything's u's, no x's. And so we can go ahead. And then also, so you got this. So pull the 2 all the way out in the front. And then u to the 8th times u minus 1, that's going to be u to the 9th minus u to the 8th. Du. Okay, and then I can integrate those. U to the 9th, the integral of u to the 9th is u to the 10th over 10. And u to the 8th is u to the 9th over 9. That's evaluated from 1 to 2. Okay, so putting a 2 in, we have 2 to the 10th over 10 minus 2 to the 9th over 9. And then subtracting and putting a 1 in, we have 1/10 minus 1/9. Okay, I simplified this using a calculator, and I got 4,097 over 45. Okay, great. Any questions about this? Okay, so this is kind of a weird thing, and it's kind of hard to see that, because usually when you're looking at things, when you're doing a U-substitution, the important thing is that you have to account for everything. Usually with a situation like this, if it's a U-substitution, you'll have some kind of form of the derivative of this inside part, which would be the derivative of the square root that's sitting out here somewhere that you can tap into. But here you didn't, but it didn't matter because we could do this way and then just go this way. Okay, this next exercise is really challenging. Dx over x times the square root of 10x plus 49. Okay, this one is very challenging. It took me a few tries to figure this out, actually. But here's what you can do. We're going to do a U-substitution, okay? But it's kind of weird U-substitution. So we're going to let U be the square root of 10x plus 49. Or let me write it this way instead. 10x plus 49 to the 1/2, okay? So that means that du is going to be, okay, so taking the derivative here, is going to be, so you have this 1/2 coming down, I mean, and then 10x plus 49 is reduced by 1 power to negative 1/2. And then you take the derivative of this inside part, so you have a 10 coming out, okay? So du is actually going to be 5. Wait, 5, and of course the dx on the end. It's going to be 5 over the square root of 10x plus 49 dx. Okay, and so what? So let's take this 5 over to here. And actually, what I'm trying to get at right here is that all of this gets replaced with a du over 5, actually. Okay. Okay, so all that got replaced with du over 5. Okay, right here, because that's what it's du over 5 is. Okay, now the other thing is this part right here. If I square both sides, I get u squared is 10x plus 49. So that means that 10x is equal to u squared minus 49. So x would be u squared minus 49 over 10. And so what happens is this part right here, this is 1 over x. This one gets replaced with u squared minus 49 over 10. Okay, so this is x. So 1 over x would be the reciprocal of this, which would be 10 over over u squared minus 49. Okay, and so now we have the integral of 2 du over u squared minus 49. Okay, and then at this point, what kind of an integration does this look like?
Partial fractions.
Yes, exactly. Partial fractions. Okay, so let's go ahead. So we just run partial fractions on this. So this factors into u minus 7 and u plus 7. Multiply everything by this, you get 2 equals a times u plus 7 plus b times u minus 7. Set u equal to 7, and that gives you that goes away. This becomes 14, and so a is going to be 1 over 7. Okay, and then if you set u equal to negative 7, that goes away. This becomes negative 14, so b will be negative 1/7. Right there. So the integral now becomes the integral of 1/7 over u minus 7 minus 1/7 over u plus 7 du. Okay, that's because this is our a and that's our b. Negative 1/7 is our b. And so we can integrate this. We have 1/7 natural logarithm of u minus 7 minus 1/7 natural logarithm of u plus 7 plus our constant. And then, of course, we need to substitute back. So we have natural logarithm of the square root of 10x plus 49 minus 7 minus 1/7 natural logarithm, and then you put in u also is the square root of 10x plus 49 plus 7. And then, so this would probably work out as an answer, or you could put it as, because you can factor 1/7 out and you'll have log of this minus log of that with no thing, and then log of, and so then you can write it as a fraction. Okay, so that's just exploiting log of a minus log b equals log of a over b. That's just exploiting that.